Hello, everyone, and welcome to Office Hours with the Meter Environment team. Today's session will focus on the LABROS instruments and how they work together. And we're shooting for about 30 minutes of Q&A with our experts Rivera and Shaun Weldon, whom I will introduce in just a moment. But before we start, one housekeeping item. If you're watching this video and you think of a question you'd like to ask our science experts, we encourage you to submit your question on our website at metergroup.com. And then someone from our science and support team will get back to you with an answer via email. All right, with all of that out of the way, let's get started. Today, our panelists are application specialists Leo Rivera and Shaun Weldon. Leo is a research scientist and director of science outreach at Meter Group. He earned his undergraduate degree and master's in soil science at Texas A&M University, where he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Leo is the force behind application development in meters hydrology instrumentation, including the SATURO, HYPROP, and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. Shaun Weldon operates as the SATURO, HYPROP, and tensiometer product manager at Meter Group. He has over 7 years of experience helping researchers measure the soil plant atmosphere continuum. So thanks for joining us today, and let's get started.
Thanks. Excited to be here.
Yeah.
All right, so first and foremost, let's go over what LABROS is. So what is it? What instruments comprise LABROS, and how do they all work together?
Yeah. Do you want to kick us off, Shaun?
Sure. So the LABROS instrumentation is any of our non-field instruments. This includes the HYPROP, the KSAT, the PARIO, the WP4C. It's all the ones where you bring the sample back to the lab and you're going to be testing there. And they kind of all work to give us a complete picture of soil physical properties and also they're really useful for doing the moisture release curves.
Yeah. Yeah. And just to kind of build on that, the goal behind the LABROS system is to develop a set of tools that allow us to fully characterize soil hydraulic and physical properties, utilizing what we believe are the best methods available to make these measurements. And a lot of experience has gone into developing these tools. We've worked with a lot of different researchers to develop these, and now much of these are becoming the standard for making these measurements in the field.
Yeah. And one thing that I love about these is that there's a workflow that you can go from taking with a single sample. You can go get your KSAT, move it directly to the HYPROP, then take a sample to the WP4C, and then right to the PARIO.
Yep.
It's just a nice, smooth transition from each of those instruments into the other.
Yeah, no, it really is. It's just kind of building that whole system to be able to do it all together.
Yeah.
And we'll see what's next.
All right, so first we're going to cover the HYPROP, and mainly questions to start out with dealing with soil moisture release curves, and then we'll get into some more general questions regarding the HYPROP. So first of all, they're asking, this first question here is asking, how can air entry be found on a soil moisture release curve?
Yeah, well, I can start with that one. It's really easy, actually. The soil moisture release curve. Well, let's just first talk about what air entry is. Air entry is the point at which you start to see a change in water content. So it's the point at which air can actually enter the soil as the soil is beginning to desaturate, and that's the point where you're going to start to see more dramatic changes in water potential and water content to some extent. But if you look at the shape of the soil moisture release curve, it's really easy to see at the very beginning of the soil moisture release curve where that air entry begins to occur, because typically you have a very flat soil moisture release curve at the beginning. And then when air entry occurs, you start to see a steepening of that curve. And you can use those data to figure out where that air entry has occurred.
Yeah. Yeah, and that's one thing that's really nice about the HYPROP is it puts those graphs right there for you.
Yep.
You can see that point really easily.
Yeah. And what's really neat is when you have bimodal samples that have typically have a gap in their pore size distribution, you might actually see multiple air entry points. And those are helpful to know because there's other things that are occurring, like limitations in hydraulic conductivity and things like that, that are also useful information that we've learned in that curve.
This next question comes from a PhD student studying soil science who's interested in the impact of wildfires on forest soils. And they're asking if you could elaborate on how soil moisture release curve data can be used to interpret the changes in soil moisture behavior in forest soils affected by wildfires.
Yeah, that's a great question. I think the key to this is going to be having that kind of before and after data. When you have a set before, you'll be able to see exactly how that undisturbed system is handling the water, how it's holding the water and how it's releasing that water.
Yep.
A lot of times after wildfires, you'll see a decrease in that hydraulic conductivity because of the hydrophobic properties that can become because of that burnt organic matter. And so you'll be able to see those changes pretty easily by running a sample with that disturbed sample.
Yeah. And like Shaun said, you really need that previous data to be able to know what the impacts are. Because if you don't, then you don't have your baseline.
Right.
But yeah, you can look at things like hydrophobicity. You can also look at the permanent alterations that we see sometimes to the soil particles themselves, depending on the intensity of the burn. And you could even do some things with the PARIO as well, looking at particle size analysis and seeing if you see a shift in those data, depending on how that burn has altered the soils. So yeah, definitely can do some really interesting things. And you can also do some field measurements as well to look at some things. And that's what another thing that researchers do is look at some field measurements of these properties as well.
This next individual says, please correct me if I'm mistaken, but my understanding is that the porosity of forest soils can undergo temporary changes following a wildfire, primarily due to alterations in the organic content. Could you please elaborate on this phenomenon?
Yeah, I mean, Shaun kind of touched on that already. It's the biggest issue is the hydrophobicity that you see in the soils. I wouldn't say that necessarily is altering the porosity. What it's really doing is altering the wetting angle, which leads to hydrophobicity, and so that impacts the soil's ability to hold or even take on water. Now, again, I think this has to do with the intensity of the burn. But if you do see actual alterations of some of the soil particles, depending on how hot that burn is, then you might see some impacts of porosity and just the pore size makeup. But I think the bigger issue is the hydrophobicity.
Yeah, absolutely.
Next question here. I am measuring water content variation in silty soil under freeze-thaw cycles. How do you accommodate the volume changes and mechanical degradation of the soil?
Yeah, so our LABROS Soil View software is really great for estimating these kind of things. Once you have your sample taken and run on the HYPROP, for example, you can go in and you can actually account for volume changes. If you're looking at things like mechanical degradation, then the PARIO is going to be really great to see, before and after again. Before, you'll probably have those larger particles and you'll be able to see that in the PARIO. And when you run a sample after, several freeze-thaw cycles, you're likely to see those particle sizes shift more towards that finer textured soils. And that's really easy to see with the PARIO device.
Yeah, no, that's exactly right. And another thing you could do, this is a common issue in other shrink swell soils as well, is you could actually look at things in terms of gravimetric water content instead of volumetric, because then once you know what your shrink swell curve looks like, you can actually model out what that volumetric water content change looks like a little bit better. And I think to even add to that, another measurement I might recommend, which isn't necessarily something that we do, but looking at aggregate stability afterwards as well. And there are some really simple to use tools out there like the Slakes app. And that's SLAKES. It's a really cool tool for using your smartphone to do aggregate stability. It's free and it works quite well, and it's been pretty well proven in literature. So that's another piece that might be interesting to add along with the other measurements that you're doing with the LABROS tools.
Yeah. Last question regarding soil moisture release curves. This individual is asking, is it possible to develop an accurate release curve using only volumetric water content?
We actually get this question quite a bit, and we also get the other side of it too. Is it possible to do it only with water potential measurements? And the answer is unfortunately no. You're going to need both the water content and the water potential to be able to get an accurate curve.
Yep. Yeah. Unfortunately, what you're trying to do, a moisture release curve, is that relationship between water content and water potential. And you can't really get one without the other.
Yeah.
People try and do that through modeling sometimes using pedotransfer functions and things like that. But those don't always work. And if you're taking the time to make the other measurements, you might as well get both to actually get a moisture release curve.
So these last few questions here regarding the HYPROP are just going to be kind of general questions regarding how to use it, etc. So this first question is, how reliable is the fitted K unsat data of the HYPROP?
Yeah, it really depends on the sample, to be honest, because the way the unsaturated hydraulic conductivity measurements are made with the HYPROP is you're looking at a difference in water potential, or a change in water potential at two different points within a sample, and the change in water content that corresponds with that. And one of the challenges early on in the measurement is that the lower and upper tensiometers track with each other early on. And if there's no difference in their rate of change, then we can't really reliably measure the unsaturated hydraulic conductivity. And so that's typically a bigger issue in coarser textured soils. In finer textured soils, we can get really good unsaturated hydraulic conductivity data much further up into the wet range than what we could with a coarser textured soil.
Yeah. And I'll just add on there too. I think with the HYPROP specifically, but most of our instruments as well, a lot of it's also going to come down to how well you've prepared both the instrument and the sample as well. If you don't have a good degassing on your tensiometers, your data is not going to be as reliable as if you go through the process and make sure that you're getting a proper degas, you're getting that sample properly saturated, and just really doing that work at the beginning.
Yeah. Yeah. And I think to add to that, I mean, what Shaun touched on is super important, is that an instrument setup is critical. But we have tools that make it easier.
They do.
So the vacuum system and using those tools make it where these devices are a lot easier to set up. The learning curve is a lot less steep. And most people can get very reliable measurements when the tools are used together properly.
Our last HYPROP related question here. They are saying during HYPROP measurement, the tension sometimes decreases before it rises again. What is the reason?
Yeah. I mean, what I'm thinking that they're asking here is sometimes you see occasional dips in both tension readings in the HYPROP data. And this is an area that we looked at quite a bit before. I worked with researcher Leon von Passen he's back at TU Delft, I believe. And what he found, and this, I think you see this more in finer textured soils, is as the soil is shrinking, as the soil is drying, you do get slight shrinkage, even in non-clay soils. And when that soil releases from the ring, so when there's an actual physical release from the ring of the surface, or the surfaces of the ring, you actually see that that mechanical release actually causes a dip in the suction or in the water potential of the sample. And so you will actually see that in the data, and you see it in both the upper and lower tensiometers, and it's consistent. And sometimes you'll see it happen multiple times in a measurement. And so it just depends on the soil, but those are actual phenomena in the way the sample is behaving during the measurement.
Yeah.
Okay. We're going to switch gears and talk about the WP4C. This first question asks, how can I combine my WP4C data with data from my HYPROP?
This is now easier than ever. The new LABROS Soil View analysis software actually talks to the WP4C, which up until about a year ago, it didn't. So now you can actually have your WP4C on that same software and add those data points directly into a HYPROP data set that you've already collected, which is really great because it was a little bit cumbersome in the past, and I'm really glad we have this ability now.
Yeah. And it's super cool that they added that. I think this is something we've been hoping to see for a long time.
Yeah.
And beyond that, we have really nice write-ups on how to collect your samples from the HYPROP to make your WP4C measurements. So that way you guarantee you're on the same drying curve. And so you get really good connection between your HYPROP and WP4C data. So, I mean, obviously this is an area we spent a lot of time working on. And so utilize the resources that we have out there, use the software, use the guides that we have on how to collect your samples and prep them. And you'll get really good data. So,
and just to kind of put a plug in for that, then if you're still using the HYPROP Fit software, please upgrade it to that LABROS soil view analysis, because it's got the newest tools and abilities in there.
Yeah. So, and it's free. So just go download the new software.
Next question. Should I use continuous or precise mode for wet samples?
Yeah. Do you want to touch that one, or do you want me to touch on it?
Yeah, you can go for it.
Okay. It depends on where you're at. When you're getting really wet, you're going to want to use continuous mode. So if you're trying to push up above, let's just say 2 megapascals, so above minus 2 megapascals, I would recommend switching over from precise mode to continuous mode to get the best measurements. Precise mode does pretty good up in that range, but if you're really trying to overlap with the HYPROP and the tensiometer measurements, continuous mode is going to give you the best results, because then you can look and really see when things are stable.
Yeah.
But yeah, what else would you say are keys to getting those good wet end measurements?
Well, I think the biggest thing is that if you're running multiple samples, even if you're outside of that range that you just mentioned, if you're running a couple of different samples and you're noticing that it's not being consistent, then definitely try and switch to that continuous mode. Sometimes even if we're in those ranges that we recommend, there might be different soil types that might just need that extra time to equilibrate. And so that continuous mode allows you to actually see when it's stabilized.
Yeah. And one other challenge when making wet end measurements is temperature changes in the room that you're in. And so if you're working in a lab environment that has pretty big temperature changes throughout the day, it will actually impact your ability to make really good wet end measurements. Yeah. So there are ways to kind of buffer that for the device, or try and work in an environment where you have a more consistent temperature.
All right, here's a fun one. Can I use my WP4C in the field?
Please don't. No, the WP4C, like Leo was just kind of talking about here, does need stable temperature. It needs to be in a place that's climate controlled. It's not designed to be used out in the field. So it's best to keep it in the laboratory setting.
Yeah, I think that's right. I mean, if you can collect samples and bring them back, that's best. If you are going to try this, which I have seen a couple of people do this, they usually have essentially portable labs that they're working in. I would definitely not try to do this out of the back of your truck. Because of the consistent temperature, or at least a semi-consistent temperature is necessary for getting good measurements. And it does also require a decent amount of power. Yeah. So this is not something that you can just power with a battery very easily. Yeah.
You'd be surprised how many factors influence that temperature. Cloud cover changes in that will really change that temperature and can get some really inconsistent readings for you.
Yep. But if you have a portable lab, then you're good.
Okay. Next question. Can the WP4C be used to measure the water potential of plant leaves?
Yes, it can. It's actually really good at it. We have a lot of people that use it for this. We actually have a write-up on our website on how to do this method. You're typically going to want to be, abrading the leaves so that you can get that moisture release from them. There's a couple of key components to do this with the WP4C that'll make it successful. The first one is making sure that you have enough sample to cover the bottom of the cup. Yep. A lot of times, especially with smaller leaves, we'll see people allowing that bottom of the cup to show, and that messes with the temperature readings, so you don't get very good results. So if you're using small leaves, very small leaves, you want to make sure that you just have enough to cover that. And then also just making sure that they're fresh. That's the other big thing, so that you get that actual moisture release in there.
Yeah. Which almost makes you think, oh, this needs to be done in the field, but you don't want to do it in the field. And if you don't understand how the measurements are made in the WP4C, the sample temperature is measured using an infrared thermometer that's looking at the sample. So if you don't have enough sample to fill the bottom of the cup, then that infrared thermometer is looking at both the sample and the bottom of the sample cup, and that messes with the readings a little bit. So that's why we always say, fill the cup bottom of even with soil, you want to make sure you have the cup filled at least a third full to get good measurements. But yeah, this is a pretty common application, and quite a few people do this, and we teach this in our environmental biophysics course as well.
Yeah.
Our last question regarding the WP4C, they are asking, can I separate osmotic and matrix potential with the WP4C?
Yeah, you can. There's a nice equation. What it does require, though, is you need to take a saturated extract EC, a measurement of the sample, and then you need to know the water content the sample is at in terms of gravimetric. And then you can actually correct out the osmotic component. We have a nice write-up on this that talks you through how to do this. But it does require taking the saturated extract EC of the sample and then going through and modeling that. And then you can calculate that out pretty simply.
Yeah.
So, which in some cases is actually necessary when combining HYPROP and WP4C measurements, because the HYPROP only measures matrix potential, whereas the WP4C measures both matrix and osmotic. And if there is a significant enough of an osmotic component, it can cause a separation in the two measurements.
Yeah, and there's actually a couple of really great examples in that write-up that show that what that data looks like when you have that high osmotic potential as well.
Yeah.
All right. We are going to wrap up with our last instrument that we're going to cover today, the KSAT. This first question about the KSAT is asking, how is head loss handled in the KSAT software? Or is this even important in the measurement?
Yeah, that's a great question. So when you're doing the measurement in the KSAT, you have two options for your measurement. You can do your falling head, which is just going to use gravity to push the water through your sample. And in that case, some head loss is going to be expected as that water column gets smaller, and it's going to be accounted for. That pressure sensor in the KSAT is incredibly sensitive. So it will be able to calculate that rate change from that full burette down to the bottom there. For the constant head, you're actually setting that rate that the head is going down. So it's compensated for in that measurement as well.
Yeah. Yep. That is actually pretty easily to do mathematically.
Yeah.
And because you have the really good pressure measurements, it really simplifies what that looks like. Personally, my favorite approach is using the falling head in most samples, because it doesn't require any user intervention to make the measurement. And it actually, I think, improves the accuracy of the measurement, because there's always the chance of human error when you have to monitor when you're hitting certain thresholds, which you have to do that with the falling head. With the constant head. But having said that, there are, in my opinion, I think there are some sample types where the constant head is better, especially if it's a sample where you run the risk of flushing out the material.
Yeah.
With the higher pressure heads. With the constant head, you can set a really low pressure head and get a good measurement without disturbing the sample.
Yeah. And I think that, in general, the falling head is probably more representative of what the conditions would be in a soil anyway, for rainfall or runoff or even irrigation.
Yeah.
So
this individual is asking, I would like to know if your KSAT and HYPROP instruments are able to analyze soilless media. So in their case, they're particularly asking about media made mostly of peat moss and bark.
Yeah,
definitely.
We've done, oh my gosh, hundreds of samples like this now. So for sure, they're actually really powerful tools for analyzing these samples, because one, the bulk of the moisture held in soilless media is held in the range that the HYPROP measures.
Yeah.
So it's a super powerful tool for characterizing those samples. And there's many companies out there that actually use these to understand different medias that they make. They also, and as long as the hydraulic conductivity, which in most cases, it is within the range of the upper end, which is 10,000 centimeters per day for the KSAT. Is that right?
Yeah.
Then most soilless media is not going to exceed that.
Yeah.
And so, yeah, these are both super great tools for analyzing those materials.
Yeah. The one caution that I would give on this is if you do have a media that has very large particle size or chunks of wood, the most important part of the HYPROP measurement is good contact between that media and the ceramic tip of the soil.
Yeah.
So if you're not getting that, then your readings are going to be off. But if it's going to be good contact there, then you don't have any problems.
Yeah. Yep. No, and I think most manufacturers of soilless media try to avoid that now because those big chunks actually cause a really big gap in that pore size distribution that we talked about, which actually can cause issues in the availability of the water for plants, depending on how dry they get. So, but yeah, definitely watch out for that contact issue.
This next question is asking if it's possible to use contaminated soil in the KSAT. So they're looking at soil contaminated with oil, chemicals, metals, etc.
We don't recommend it. That, like we said earlier, that pressure sensor is incredibly sensitive. And whenever you're putting in chemicals, metals, or even oils, you can run the risk of getting corrosion on that pressure sensor cap. And you also run the risk of getting buildup of things in the internal compartments of the sensor, which over time are going to affect how your readings look.
Yeah. I mean, if you do wind up having to do this, clean the instrument afterwards.
Yeah.
Because you don't want to leave that stuff in the device and potentially cause issues down the road with it. And which honestly, it's a good practice anyways to clean your instruments after you make measurements. So, but yeah, you have to watch out for those things.
All right. I used the wrong parameters in the evaluation. Can I reevaluate my data?
I'd have to ask first. Is this a KSAT related? This is KSAT related, right?
Yeah.
Okay. Yeah. Can you?
Yeah, you should be able to. Once you have saved it, it will still give you, as long as you have that original data file, you can go in and you can change those parameters and resave it. However,
that's right.
Yeah.
And it can reprocess the data.
Yeah,
that's correct.
Yep. So that's, and not even specifically, KSAT, all of our instruments are set that way so that if you go in, you can actually change parameters again and play with even change models on the HYPROP and save different versions of it so that you can see which model fits your data the best there.
Yeah, for sure. And I like to spend a lot of time messing around with those models to find the one that best fits because different samples have different shapes to the curves and certain models don't behave well with certain shapes. And so you definitely want to take time to find the best model that fits your data. Now, having said that, depending on how you're using the data, you might be limited to certain models,
right?
And have to use those. But ideally, you can kind of work with some of the ones that give you a little more flexibility.
Mm-hmm.
So this next individual is asking, how can temperature change or influence the results of measurements?
Yeah, that's a really good question. Temperature impacts everything in measurements. Mm-hmm. And when we're thinking about hydraulic properties, one of the big areas where temperature influences things is the viscosity of water. So as temperature decreases, the viscosity of water increases.
Right.
And what that means is it actually will slow down how fast it moves through the sample. But the KSAT actually normalizes the temperature.
Yeah.
Or it normalizes the KSAT for temperature.
Right. So normalizes it to 10 degrees C. So all of your measurements are going to be normalized to that value. So you won't see the influence of those temperature changes as much.
Yeah. So it's really nice to be able to do that, especially when you're comparing across multiple. If you're making measurements across a long period of time, you might see differences in water temperature and all these things. And so it makes it easier to do comparisons over time of different samples, and work with that. And and it's something that even in field measurements, you have to consider as well. It's just a little more challenging to deal with that in the field than it is in the lab.
All right. That's going to wrap it up for us. Thank you again for joining us today. We hope you enjoyed this discussion. Thank you again for everybody that has submitted such great questions. And again, if you do have any questions that we didn't answer, please contact us via our website, metergroup.com. Finally, subscribe to the Meter Group YouTube channel and accept notifications to see previous episodes of Office Hours and to get notified when future videos are available. Thanks again, stay safe, and have a great day.